Hello and welcome back to Starting Out with Quantum Computing. I'm your host Lloyd, and I think I have an interesting one for you this time. So we're talking about the Pauli Exclusion Principle, and it really confused me up until now. There was an Austrian physicist and Nobel Prize winner called Wolfgang Pauli, and he devised the Pauli Exclusion Principle in 1925, over a century ago. It's a quantum mechanical rule which explains numerous phenomena that occur in our universe. But before I dive into that, allow me to set the scene for you. It was a rather normal day at work for me. I was sitting, reading a paper about nuclear physics. All was well, and I was happy. And this paper went on to talk about how nuclei form. In particular, it described the formation of weakly bound nuclei, which are nuclei which have nucleons that can be removed with very little energy required. As I read on, I learnt for the first time that the reason why these nuclei remain bound, or just about, is due to the delicate balance between the strong nuclear force and the Pauli exclusion principle. The strong nuclear force, which is, by the way, the most powerful of nature's four fundamental forces, is responsible for gluing protons and neutrons together. Without it, nuclei wouldn't exist, and neither would atoms, neither would people, for that matter, which are made of atomic nuclei. Although on the surface this seemed fine, something didn't feel quite right. The strong nuclear force is, of course, an attractive force, yet the Pauli exclusion principle is most certainly not a force of any kind. So then how is this principle able to physically counteract the attractive nature of the strong force, leading to weakly bound nuclei? And to answer this question, I would need to consult the man himself, Wolfgang Pauli. Wolfgang Ernst Pauli was born in Vienna in 1900. His father was also called Wolfgang Pauli, confusingly, and his mother Bertha Schutz. Wolfgang's middle name, Ernst, is rather iconic, as it is taken after his godfather Ernst Mach, the inventor of Mach number. You might have heard in movies about military jets going past Mach 1 speed or Mach 2. Just 2 months after graduating from secondary school with a distinction, Pauli published his first paper on Albert Einstein's theory of general relativity. And he would then go on to study for a PhD under Arnold Sommerfeld, a prominent German theoretical physicist whose research is foundational to current quantum mechanics and atomic physics. After receiving his PhD in 1921, Pauli spent a year at the University of Göttingen as Max Born's assistant, another renowned physicist. It was when he became a lecturer at the University of Hamburg between 1923 to 1928 that he would develop the Pauli exclusion principle, one of the most important rules in quantum mechanics. But let's continue Pauli's story quickly. Pauli was appointed professor at ETH Zurich in 1928, and he was awarded the Lorentz Medal in 1930. That's a very big award. Decades later, he was awarded the Max Planck Medal, but fell ill with pancreatic cancer that same year, dying in December 1958. However, his important contributions to the field of quantum mechanics lived on and have become a cornerstone in our knowledge of the quantum world today. There is also an interesting story regarding his last moments in Rotkreuz Hospital in Zurich. Throughout Pauli's life, he had been chasing a particular number in his research. This infamous number was the fraction 1 over 137, which is nearly exactly the value of the fine structure constant, a dimensionless constant that quantifies the strength of the electromagnetic interaction between charged particles. When his last assistant, Charles Enns, went to visit, he asked Charles, "Did you see the room number?" It was 137. So, the Pauli exclusion principle, put simply, is no two fermions can exist in the same quantum state. That's genuinely it. This is what Pauli proved. It's simple, but it has incredible consequences. To be a little more specific, the full principle states that multiple fermions, which are particles with half-integer spins, such as the electron, cannot occupy the same quantum state. It would probably take too long to discuss what makes a particle a fermion, but simply think of fermions as things such as electrons and protons and neutrons. Pauli was able to derive this phenomenological rule based on atomic spectroscopy experiments of the time. These experiments showed phenomena that could not be described by the latest atomic model theories. Although his proposal of electrons obeying this exclusion principle came first in 1925, he would generalize this to all fermions with his spin statistics theorem in 1940. So when does this principle physically come into play? Where do we see it cropping up? Well, in many scenarios, actually. The Pauli exclusion principle helps explain the electron shell structure of atoms, as well as the way atoms share electrons when they bond. This can inform us of the size and structure of the elements of the periodic table. It also helps us figure out the chemical behavior of the elements, such as which elements are more or less reactive, or which will react with others. Secondly, the principle helps us to understand the properties of conducting metals, for example, the very copper wires which power our homes. You can use the principle to understand why metals are conductive, insulating, or semiconducting. And thirdly, the principle also has consequences for astrophysics. For example, it can impact white dwarf stars, which are essentially dead stars. When stars die, gravity tries to collapse all of the matter into the center, but due to the fact that electrons can't occupy the same state, the exclusion principle counteracts this and prevents further collapse. And so this was how my confusion was finally removed. There are only 4 fundamental forces, so far at least in quantum theory. There are only 4 fundamental forces in the universe, and the Pauli exclusion principle isn't one of them. These forces are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. They are considered fundamental at every single They are considered fundamental as every single interaction that occurs in the universe can be accounted for by one of these 4 interactions. These 4 forces, they cannot be simplified or broken down into anything more basic. Another condition for a force to be a force is that they must be mediated by exchange particles. In other words, there must be some sort of carrier particle that carries the force and enacts the force upon matter. The only exchange particle to have not been detected yet is the one for gravity, which has been called the graviton. What this means, therefore, is that the Pauli exclusion principle is more aptly named a pressure. This is why we often refer to the effect of the principle as degeneracy pressure. There is no exchange particle for the Pauli exclusion principle, and it is most accurate to consider it as a fundamental constraint. Nevertheless, the principle causes particles to repel from each other, producing a repulsive force at a large scale. To conclude, the Pauli exclusion principle is a pressure that produces a force. I rest my case. Thank you very much for listening to Starting Out with Quantum Computing, and I very much look forward to seeing you in the next episode. Thank you very much. Bye-bye.